Hey folks, so in this video, I'll introduce the idea of a linear probing hash table. So what's the basic idea? So again, we're going to have an array of size m, right? And m, it's pretty standard, right? But here we're going to have a little bit of a kind of an important note here, which is m needs to be at least as big as n. And maybe ask yourself why. Well, you could ask yourself why is the case, but maybe you don't know about enough. We'll come back to that question in a second, actually. So imagine you have an array of size m, right? And this array, right, we're just going to leave it alone. We're not going to populate it with lists. At each index, we're going to put a single key value pair. Okay, so when we are, basically using our hash functions, we're going to use our hash function, right, to produce the hash to then get the index. And we want to add something. We're basically going to go to that index and put the key right there. Done. Well, I guess provided that it's empty. You can use the index directly. Otherwise, if the index is not used, then we need to move basically one element forward to the right and put it in that slot. If that slot next door is empty as well, then we basically move one more. It's like we're basically going to start at one point and move to the right until we find an empty space, right? Hopefully we get lucky and it's the first place we look, but maybe we don't, in which case we have to go and search for one. So this is the fundamental idea behind linear probing. Start at an index, fill it, or move to the right if it's not filled. Put it as close as you can to the index it wants to be in. All right, so jumping back up there, the question was, why in linear probing must m be at least as large as n? What do you guys think? Well, the reason is, I only allow, right, one key value pair per index. So I need to have at least enough indexes to correspond to the number of, I need to have at least enough indices in my array to correspond to the number of things I want to insert. Right? Otherwise, I'm sunk. Right? I'll have to, throw away something, right, or override something. I don't know. So m has to be a decent size. For something like a chaining approach, we don't really care because in a chaining approach, we have lists at every position, and so it's like, oh, I can just add into those, right? Lists basically, I can add as many things as I want, right? So it was fine. Here we're using just an array, and an array has a fixed size. So we do have to be a little bit careful. In general, we're going to have to actually spend some time and energy basically to maintain m as being appropriately larger than n. Otherwise, we get into all sorts of issues. All right, so talking about the basic concept, let's take a look at this little bit of a trace on the right-hand side. So we have initially, right, an array, and we're saying it's of m equal 4 size. And we're going to have, again, this very, very simple hash code, right, which is basically, there's no really hashing work to do. We just need to finish it off with doing a mod 4, right? Do modules by the size of the array to get the actual index. So let's see. Initially, let's say I want to insert basically the key 0. What happens to it? Well, 0 mod 4, index 0, right? So 0 wants to go to index 0. That's fine. Good stuff. Then we go to 1. 1 wants to be added to the array. So it gets, basically hash, and it wants to go to the index of 1. Okay, that's fine. 1 is, free over here, right? We're looking over here and saying, are these free or not? 1 is free, so I can put it in there. All's good. Then we go to 4, and for 4, right, that's going to hash basically to 0. Okay, now things are a little tricky because I want, right, to basically put that number 4 in index 0, but index 0 is already full. So what do? I start by looking at it. I say, hey, this thing is full. And I go and look at its neighbor, which is 1, which is also full. And then I look at its neighbor's neighbor, and that would actually be a blank space. So then that's where I'll add this thing, right? So actually, wasn't able to add it at where I wanted to or the place next to it. I had to go 2 away from it, and then I got, an empty space. So that's where the 4 ends up. Then for 5, right? For 5, we wanted to insert the number 5. That wants to go into array index 1. That means we basically start by looking over here. That's full. Then we'll go to the next one. That's full. Then this over here is empty. Add the 5. Okay. So basically, it's like start at an index, right? Try to put yourself there. Otherwise, start moving to the right. Find the next empty one and add yourself there. All right. So that's the basic concept of this kind of technique for storing data. In the next video, we'll do kind of a sample trace of running this algorithm for kind of a larger set of data.